Hi, this is Mr. Anderson, and in this podcast, I'm going to talk about matter. What is matter? Matter is anything that has mass and takes up space, and so we'll say that it has a volume. Now, scientists got together and they decided to think about, what was the greatest discovery of the last 100 years? And they eventually came up with this discovery by this scientist named Hubble. And what Hubble discovered is that no matter where he looked in the universe, everything in the universe is redshifted. That means everything is moving away from everything else. And so if we play that backwards through time, what that led us to is this point at which all matter began as a single point. And so that's where we got this idea of a Big Bang, and that there's been this expansion of the universe. But what is that universe made up of? Matter. A lot of it's actually dark matter, but that's a totally different story. This is a cool side note. This is called aerogel, and so this is it's a solid, but it's an incredibly low density solid. And it's actually made by making a gel and then replacing that liquid inside there with a gas. And so here's cool. It's insulating this flower from a Bunsen burner, which I think is pretty amazing. So we'll talk about states of matter in here as well. So what is matter? Matter can be broken down into two things. It can be broken down into what are called pure substances, and then it can be broken down into mixtures. And so everything you think of, from myself to the air that I breathe, is one of these things. And so the first one is going to be a pure substance. And so example, this is helium gas. Helium gas is made up of only one atom, and so we call that an element. Carbon, for example, carbon in a pencil that you might be using, is also an element. It's only made up of one type of atom. As we move up the level in pure substances, we can also have what are called compounds. And if you have something that's made up of, for example, one or more atoms that are put together in a specific ratio, 2 or more, then we have a compound. And so some things that you're familiar with would be like H2O or water. So the water in this droplet right here is made up of 2 hydrogen atoms and 1 oxygen. Or the glucose that's inside this plant right here is actually a compound as well. And so pure substances are simply elements and compounds, but they have to be pretty pure, and that's where they get their name. Next, we have what are called mixtures. An example of a mixture, one of my favorite mixtures, would be soda. This is actually Mountain Dew. Inside here, if we could look inside the can, that would be a homogeneous mixture. Homogeneous mixture means that you can't tell apart the different parts inside it. And so if you were to look inside Mountain Dew, there's going to be water, but there's also going to be carbon dioxide, and there's also going to be sugar, and there's also going to be caffeine, and there's going to be yellow dye, number 5, and all those things are mixed together, but you can't tell the different parts. So we call that a homogeneous mixture. Now, most everything that you're used to dealing with in life, like me or the computer sitting in front of you or anything, is not going to be that. It's actually going to be a heterogeneous mixture. Heterogeneous mixture is when you can see the different parts. And so this is blood. And so we might think blood looks like a homogeneous mixture, but when you get down to the level of blood, we can see red blood cells, white blood cells. We could even get down to the level of platelets if we looked at it. And so that's a heterogeneous mixture. So that's how we classify everything. Now, this is a great diagram because it shows you in the universe, this shows you the atomic number. So we're going all the way from the first, hydrogen, all the way up here to uranium on the far end. This is how much they naturally exist in the universe. And what you find is that we have a lot of hydrogen and helium. We don't have so much beryllium. And then we have these points that kind of level up as we go through the atomic number. Now, this is a log scale. That means we have a whole bunch of hydrogen and helium. And you might be thinking, I wonder why that is. Well, the sun gets its energy from hydrogen fusing into something called helium, and that gives off a huge amount of energy. If you've heard of this before, E equals mc squared. This is Einstein's Einstein's equation. Relates energy and mass. And the cool thing about it is when we convert hydrogen to helium, we actually lose a little bit of mass. But where does that mass go? That mass is converted to energy. And it's the energy that's giving me the sun in this room right now. Okay, so the idea of atoms and molecules came from the Greeks. And there was this guy named Democritus. And Democritus said that we could break down all matter into these small little tiny bits if we kept cutting it. And he coined that term atomos, which means to be uncuttable or undivisible. Now, on the large scale, elements, compounds, all have different states of matter. And so states of matter are linked to the kinetic energy of a molecule. And so if we look right here, the ones that you're probably familiar with are going to be solids. And so we could think of this right now as like ice in this beaker. As we start to add energy to it, those water molecules will actually move around, and so that forms that next state, which is going to be called a liquid. And if we give enough energy to it, then this is going to be water boiling, or these elements are boiling, and so they're eventually jumping off into a gas. And so you're probably familiar with those three. So if we decrease the energy, then we can go right back to a solid. Now the two ones on here that I think are pretty cool are plasma. That's when we get a gas really excited and it starts to ionize, so it starts to give off electrons. Then we form something called a plasma. Where have you seen a plasma before? You'd see that like in stars, but you also see it like in fluorescent lights. So that's a state of matter that you're maybe familiar with. But what happens when we really cool it down? When we really cool it down below a solid, we form something called Bose-Einstein. Let me try that again. Condensate. And so it was predicted by these two scientists, Bose, who was Indian if I remember, and then Einstein, who was German. And what they predicted is that when you really cool stuff down towards near absolute zero, weird stuff is going to take over. And so this really wasn't tested until 1995, when a couple of scientists at the University of Colorado actually were able to use lasers to cool stuff down towards near absolute zero. And what they found is that when you cool it down, the Heisenberg uncertainty principle takes over. And what does that mean? Well, when you slow down those atoms, you know specifically where they are. And according to Heisenberg's uncertainty principle, when you know something is, where it is, you don't know anything about its momentum. So you get this weird spike where you don't even know where the atoms are. And that's pretty wild, and that's quantum theory. But again, there are 5 states of matter. Going from energy, we go from plasma, which has high energy, all the way down to this Bose-Einstein condensate. But movement between those, we've got terms for those. So what happens if we take a gas and turn it to a liquid? You're pretty familiar with that. We call that condensation. Whereas likewise, if we vaporize, it moves up to gas. And so I love this diagram here because it shows all of those. But remember, as we increase the energy, then we're going to move up into different states of matter. How do we measure matter? We could measure it directly, and so we could put it in, for example, a graduated cylinder, and this is the meniscus, and you measure it along that point. We could actually calculate it using volume, or we could use displacement, where you measure the amount of water, you put an object inside it, and then we measure how much it displaces the water. So we could measure directly matter, but also remember that we can measure it indirectly. How do we do that? Imagine if I take a cup of the earth, and let's say that the earth was homogeneous. If I take a small portion of the earth and figure out the mass of that in grams for a specific volume, I could then, let me scratch that, if I take the mass of a small bit and the volume of that, that's going to equal the mass of a large volume. And so, for example, if I have a small volume, we'll call that mass 1 and volume 1, and I want to figure out how much the earth weighs, all I have to know is the volume of the earth, and then I can use the factor label method to figure out the mass of the earth. And so sometimes in science we can't measure really large things and really small things. And so instead of measuring it directly using a scale or a graduated cylinder, we actually have to resort to math. And we use ratios to figure out how much it weighs or how big it is. And so I think that's it. Where do we find matter? And we'll do this in the next few podcasts. We find it on the periodic table. And so the periodic table organizes all of those pure substance elements that we have into an organizational chart that also shows us properties of the matter. And so that's just kind of an introduction to matter, and I hope that's helpful.